Welcome back. Let's look at this algorithm called the sieve of Eratosthenes. I hope I'm pronouncing it correctly. Okay. This is a very beautiful algorithm. So suppose you want to find all the primes less than 125. Write down all your integers starting from 1 until 125. What do? We first remove 1 because 1 is not a prime, and then remove higher multiples of 2. What does that mean? You remove 1, you keep 2, but higher multiples of 2. So 4, 6, 8, 10, 4, 6, 8, 10, and so on. You remove all the higher multiples of 2. So notice how you're poking holes in your list of numbers. That's the sieve part. You're poking holes in your list of numbers. So you have removed higher multiples of 2 until 124. Next, remove higher multiples of 3. Okay, so you're poking more holes. You keep 3 but remove 6, 9, 12 and so on. 12 was anyway removed. Basically whatever was left over. Okay, so higher multiples of 3, here is 9. 9 gets removed, 15 gets removed, 21 gets removed, and so on. Keep going. Next, you remove higher multiples of 5. Keep 5, but whatever was here, so start with 25, right? 25, 35, so on, 55. Remove those. After 5, remove higher multiples of 7. Looks like by mistake I have removed 2 here and 3 here, right? So you need to keep 2 and 3. All right, 2, 3, 5, 7. Okay, good. Now remove higher multiples of 7. So keep 7 and keep the ones which you had already kept. Okay, don't remove the primes. That's the point. Keep the first multiple, that is 2 times 1, 3 times 1, 5 times 1, 7 times 1, but remove the higher multiples. Okay, after 7, keep 11 and the higher multiples. Okay, and for 11, you see 11 times, all those earlier ones are gone. 11 times 11, 121 is the only one that you had to remove. And 121 was so close to 125 to begin with. Now notice whatever is left, they are all primes because 13 times 2 is 26, which was already removed as a multiple of 2. Okay, so 13 times 3 was removed as a multiple of 3. 13 times 4 was removed as a multiple of 2. 13 times 5, so on. 13 times 11, well, that's too far. It's beyond 125. So on. So likewise, 17 times 2 was removed. 17 times 3 was removed. The earliest multiple is 17 times 17, which anyway is beyond here, or 17 times 11 is beyond here. So whatever is remaining, these are primes. That's the sieve of Eratosthenes. Okay, it's a beautiful procedure. Here is a beautiful theorem. There are infinitely many primes. Well, prove this by contradiction. Suppose there are only a finite number of primes, P1 through Pn. Suppose you had only a finite number of primes. Then consider the number P1 through Pn, add 1. The product P1 through Pn, add 1. Notice P1 is not a divisor of Q, because if I were to divide Q, P1 would divide this one and remainder remains. Likewise, P2 divides this and some remainder remains. All these. So you said initially we agreed that there were only these many primes. Well, remainder remains. That means these primes do not divide Q. Q is one more than the product of them. So you found a larger prime. That's a contradiction. So there are infinitely many primes. Since there are infinitely many primes, over the centuries, people have tried to study different kinds of primes. Here is a beautiful example, Mersenne primes. Mersenne primes are primes which can be written in the form of 2 to the prime minus 1 for some prime. 2 to some power prime minus 1. So let's list a few Mersenne primes. When P is 2, 2 to the second power minus 1 is 3. That's a prime. So that 3 is a Mersenne prime. 7 is also a Mersenne prime. 2 to the third power minus 1. 3 is a prime. 2 to the third power is 8 minus 1. 31 is a Mersenne prime. 2 to the fifth power is 32 minus 1. 127 is a Mersenne prime. 2 to the seventh power minus 1. Okay. Next, we discuss GCD. Okay, greatest common divisor. Let's come to this in our next video.